Okay, so we are going to review circuit analysis. We've actually already done this completely through lab and various things that we talked about in class, but now we're moving into the circuit chapter, so we will review circuit analysis. So what this basically means is the application of Ohm's law, or the definition of resistance, R equals V over I, or therefore, right, V equals IR. Whoops. Now, as always, you've got to understand what this means. This doesn't, in general, V equals IR does not apply to every situation. It applies to the potential difference, and this is potential difference. It's just you usually see it as a V, not a delta V. Potential difference across a resistor is equal to the current through that resistor times the resistance of the resistor. We don't usually write it with the sub-Rs, but that's important to understand. For example, if I have a battery which has a potential difference delta V attached to some arbitrary set of resistors, and here I've got two in series in parallel with one, that delta V across each of these individual resistors is not necessarily equal to delta V across the battery. So whatever delta V across this is, and whatever delta V across this is, and whatever delta V across this is, then those equal the current through that resistor times that resistor. So we'll call this R2, this R1, and this R3. And so it does not say that delta V of the battery equals I times the resistance. It says that delta V across the resistance equals I times the resistance. That's just a quick overview. We'll come back to that. And the other part of circuit analysis is Kirchhoff's rules. So remember what Kirchhoff's rules are? There's one which is the loop rule. And the loop rule says that the sum of all the potential differences through a closed loop equals 0. Again, just as a reminder, what that means is regardless of what kind of circuit you have, let's just take the same circuit I drew, which is two resistors in series in parallel with one, that if we sum the potentials around any closed loop, then they must equal 0. So for instance, the battery gives us a positive potential. If we go in that way across the battery, we go from negative to positive, so we get a plus delta V. And then as we go around this closed loop, let's just do the bottom loop. We've got, and again, if this is R1 and this is R2 and this is R3, then we've got minus I1 R1 minus I2 R2. I didn't leave myself enough space, equals 0. That's the closed loop. That's this loop here, going around that loop. If we were instead to go around that loop, I know it's a little messy, then we would get starting from, if we start from here, we don't have to start from there, we can start wherever we want, but if we start from here, we get plus delta V as we cross the battery, and then we go, wires have no change in potential. As we go through the resistor in the direction that the current is going through the resistor, then we've got minus, the resistor uses a potential difference of I3, R3, and then we go through nothing else, and we get back to where we started, and so we get that. So that's Kirchhoff's loop rule, and then there's Kirchhoff's junction rule. Right, the junction rule says that if current comes to a junction, that all the current in to a junction equals all the current out of a junction. The sum of all the current into a junction equals the sum of all the current out of the junction. I guess the in and out maybe should go on the I. But in any case, so again, let's take the same circuit. Two resistors in series in parallel with one. And there's current leaving the battery here. And then there's current I1 that goes through that resistor, current I2 that goes through that resistor, and current I3 that goes through that resistor. Well, at this junction, right, a junction is where there's a split. At this junction, then all the current into that junction, which is just I is the current into that junction, must equal the current out of that junction. The current out of that junction is I1 and I3. So I equals I1 plus I3. What is I2 though? Is I2 and I1 coming out of that junction? No, actually, right? Since really I2 is the current through resistor 2 and I1 is the current through resistor 1. And what you have to recognize is that there is no junction between resistor 1 and resistor 2. So I1 is equal to I2, right? But the current coming out of the junction, that junction there, the current coming out of that junction is just I1 across the bottom wire and I3 across the top wire. Okay, so that's the junction rule. So using those three rules, Ohm's law and Kirchhoff's two rules, we should be able to analyze any circuit. And we've already done that, but we're just going to basically review and do some more complicated circuits. Let me start with the one that I've been drawing all along, which is two resistors in series, which are in parallel with a third resistor. And let's call these resistors R1, R2, and R3, as we have been, and the battery, or power supply, has potential difference delta B. Now, what is in series and what is in parallel? We got to remember that series means that you are connected by a single wire with no junction. So R1 is in series with R2. And parallel means that you've got two similar connections. So R1 is not in parallel with R3 because it does not have two similar connections with R3. R2 is not in parallel with R3 because it does not have two similar connections with R3. Right, in order to have two similar connections, right, so if there was a wire here, now R2 would have this connection here and this connection here, right? So there would be two similar connections, but that was not the circuit that we were looking at. So R1, neither R1 nor R2 are in parallel with R3, but the combination of R1 and R2 are in parallel with R3. What we mean by that is if we look at the equivalent R1 and R2, that is in parallel with R3 because iPad. iPad, stop it. Hold on. Okay, so because this, it's still doing it. So this side of that pair has a wire in common with R3. This side of that pair has a wire in common with R3. So these two resistors together are in parallel with R3. So we can write an equivalent circuit as this. So we've got delta V, and this is R equivalent 1, 2, right? 1, 2 in equivalent and R3. So the R1 and R2 in series, that pair is in parallel with R3. And so we could, if we wanted to, if we wanted to for circuit analysis reasons, if we wanted to figure out, for instance, how much current is being drawn from the power supply, we could go one step further and say, okay, so R equivalent 1, 2, R equivalent 1, 2 is equal to the two in series, which add. And then these, that's goes up there. And then that circuit has the equivalent of the whole circuit, which is these two, I'm pointing, you can't see. These two are in parallel so that R equivalent, 1 over R equivalent is equal to 1 over R3 plus 1 over what we called R equivalent 1, 2. And so that's the equivalent there, and that's what would allow us to determine the current from the power supply. And so then we could go backwards and figure out other things about the circuit. Again, I'm just doing a quick overview, and then we'll do some examples. But the concept I'm getting at here is what it means to be in parallel and what it means to be in series. In series, you've got to have one wire, only one wire in common, and with no junctions on that wire. In parallel means you have two wires in common. The two things that are in parallel have two wires in common. It may be that you have neither parallel nor series, right? So again, in this original circuit, R1 is neither in series nor in parallel with R3. R2 is neither in series nor in parallel with R3. You may have an entire circuit where nothing's in parallel or in series. I just drew this random circuit here, right? And none of these resistors, if we call this R1, R2, and R3, none of these resistors are in parallel with each other because none of them have two wires in common. Not even any combination of the two resistors is in parallel, or no equivalent combination, because to be equivalent, you have to have something in series or in parallel that we can call the equivalent. There's nothing in parallel, nothing in series. Nothing has a single wire in common with no junctions. How would we analyze this circuit? Well, we would still analyze this circuit with V equals IR and Kirchhoff's rules. So, for example, we could apply Kirchhoff's rule in that loop. We could apply Kirchhoff's rule in that loop. This is, this was a completely random circuit. And we could apply Kirchhoff's rule in that loop. Let's call this loop number 1, this loop number 2, this loop number 3. So in loop number 1, we would have delta V minus I3 R3 equals 0. In loop number 2, we would have delta V minus I1 R1 minus I3 R3 equals 0. And in loop number 3, we would have delta V minus... I called two resistors R3. You saw that. I didn't. Hold on a second. Let me fix it. Okay, I changed the you can see what I changed. I changed the one of them that was R3 to R2. Okay, back to, so I was doing loop number 3. Loop number 3 minus I3. Oops, okay, hold on. Boom, boom, boom. This was I2, R2, I2, R2. And then I3, R3 equals 0. So no matter what circuit you have, whether you have equivalence or not, sometimes equivalence can help you if you go back. If you can write equivalence, it can help you calculate things, but you never have to do equivalence because you can just do Kirchhoff's rule for every loop. And then we can say, and by the way, here what was given to begin with was R1, R2, and R3 and the power of the battery. And we might ask for, say, what is the current through each of the resistors? And so we wrote down, using Kirchhoff's loop rule, the three of the loops. There are actually more loops we could deal with, but I just chose those 3 loops. And we can also think about the currents. Let me draw the currents in black, let's say. So this is I1. This is I3. I haven't left for myself. Not I3. Why do I keep doing that? I2. And this is I3. Shoot. I3. And now we can look at each of these junctions, right? We can look at each of the junctions. Now, where? So we could talk about the current going from the battery, which we would just call I. And we can see at the junction on the right, where I put a yellow dot, we've got I3 and I2 coming into that junction and I going out of that junction. So I equals I2 plus I3. Now we've got an interesting situation here, which is that we've got this wire here, which I just made yellow, which we don't know what the current there is. We would really have to say that current is, it's neither I nor I1 nor I2 because there's a junction and things can split. So we'd really have to call it I4, something else, I4. And so now we have determined the current in every wire. No, we haven't. This was a random circuit, and I was just sort of showing how you would analyze it, because we now don't know the current in this wire, because there was a junction from I4, and I1, so we would have to call that I5. Again, I'm not saying we're going to finish analyzing this circuit, but now we can look at, for instance, and I'm just showing that like you can analyze any circuit. Let's go ahead and look at that junction there and say that at that junction there, the one at the bottom middle, I comes into that junction and I4 and I5 go out of that junction. And then we could look at that junction over there, the one on the left, and say I5 comes in and I3 and I1 go out. I5 equals I3 plus I1. And then we can look at the last junction, which is that junction right in the middle of the circuit there. And you got I1 plus I4 going in equals I2 going out. I4 was going up. And so that was kind of a bizarre circuit, but basically I just wrote down the junction rule at every junction, the loop rule for each of 3 loops, and there are actually more loops that we could deal with. That is enough information because there's 1, 2, 3, 4, 5, 6, 7 equations, and there's only 6 unknown currents currently, 6 unknown currents. So it's solvable, and we could solve it if we wanted to solve it. I do want to point out in this, and it's solvable. We could solve for the current everywhere. Okay. I do want to point out in this unusual circuit something. Okay, 2 things to notice. Okay, I just redrew the circuit to the right. I left the messy one on the left and redrew the circuit to the right. First thing is, let's do the loop rule around yet another loop. And the loop rule around the loop that I'm showing in with the red circle, with the red arrowed circle, tells us that there's a wire that, whoops, come on, why is it not drawing? As I travel along this wire, there's no changes in potentials. The only place there's a change in potential is as I cross R1. So if I go around that loop, all we get is minus I1 R1, because I'll talk about the sign and the direction in a second, equals 0. There's nothing, no other potentials in that loop. So what does that tell me? That tells me that I1 equals 0. That tells me that there is no current going through R1. And if you think about this circuit and you think about, and you look at it, that might make sense. I'm not sure that there's no current, but it comes from Kirchhoff's loop rule. I was thinking that if you trace the current coming out of the battery, that the current is going to go that way, and there's really no reason. Yeah. Here's the thing. I couldn't think of exactly what to say, but that this wire in the middle, which I didn't cross out, I just identified with a cross. That wire in the middle is shorting the current going to R1. If that wire was crossed out, now current would have to go through R1 and R2. But that's shorting, right? It's called a short, and it makes the current just go through R2. The reason why we know that really is, I guess, more than anything, just by applying Kirchhoff's loop rule to the loop on the left and showing that the current through 1 must be 0. Okay, let's just talk about the directions of currents. So I'm going to do one more thing with this. So you'll notice as I've just been giving these sort of examples that I've just been drawing the currents in a sense in some arbitrary direction. I'm just guessing at the direction of the current through a resistor. Now, how do we know when we do Kirchhoff's loop rule that whether we do a plus or a minus through a closed loop? We know that when we go the correct direction through a battery, when I say correct direction, we're going from minus to plus through a battery, that the battery adds potential to a circuit because it pushes current in that direction. And we know that if current is going through a resistor, so if we follow the current through a resistor, so let's follow the current through this resistor, that the resistor is using up energy. So it minus I1 R1 as we follow the current through the resistor. We could go backwards through the loop. Okay, wait, let me keep going. And then if I'm doing this loop here, for example, it would be delta V minus I1 R1 minus I2 R2 equals 0. Because we go forward through the battery and we follow the current through the resistor and follow the current through the resistor, the battery adds potential and the resistor uses potential. So hence the plus and the minus and the minus. What if I got the currents wrong? Well, let's just pretend I have them right for a moment. If I have the currents right, what if I went the other way? What if I said, let's apply the loop rule backwards? Well, that's fine. If I apply the loop rule backwards, or if I apply the loop rule and I have to go through something backwards, right? So it's just minus delta V as I go, if I were to start on the left and go to the right. If I go backwards through a battery, I get a minus sign. And if I go against the current, if my loop goes against the current, then the potential difference must be positive, right? So I2, R2 plus, and then if I go backwards against the current through, and this is again my Kirchhoff loop, right? My Kirchhoff loop. If I go against the current, then I'm adding potential when I go through a resistor, and if I go with the current, I take away potential. So obviously these two work out to be the exact same equations. So how do I know which way current goes through a resistor? I don't. I can guess it, and what you do is do exactly what I did. When you're doing circuit analysis, you just guess which way the current goes through a resistor, draw a little arrow to show that. Go back to this one. So we figure that the current usually leaves the battery that way unless something is pushing against it, which there's nothing here. So therefore, we're guessing that the current is going this way, and this way through these. If we're wrong about those guesses, when we solve for I1, if I1 equals negative 3 amps, that means we were wrong about the direction of the current through I1, and it must be the other way. That's all. So you just guess the directions, you solve, and then if it's negative, then you were wrong, it's the other way. It doesn't change anything about your solution. Your solution's still going to be correct. Okay. It's just like saying that velocity is to the right, and then you solve, and you get velocity is negative. Oh, well, that means it was to the left. Okay, so that's all the general stuff about circuit analysis. Let me just remind you what we found from circuit analysis for parallel and series circuits, and then we'll start doing some examples. So we're almost done.